Welcome to Brain Vision.
Compare the value for the density of water vapor at exactly 100 degrees Celsius and 1 atmospheres of pressure with the value predicted from the ideal gas law. Why would you expect a difference? Well, we're going to start from the ideal gas law as expected. So P, pressure times volume, is equal to nRT, and we're going to call that equation 1, and we're also going to denote the equation that relates the number of moles to the mass. So number of moles times the atomic weight, AR, is equal to mass, and that's equation 2. Now, substituting equation 2 into equation 1 and making mass over volume the subject of the equation, we have mass over volume, which is equal to rho, or density, is equal to pressure times the substituting 2 into 1, so N equals mass over AR, we get pressure times the atomic weight divided by gas constant times the temperature. And so and this is equation 3, and we know that the pressure, they give the pressure in the question. So in the question, this is at 1 atmospheres of pressure, so P is equal to 1.013 times 10 to the 5 pascals, which is the same as 1 atmosphere of pressure. And the temperature is given by 100 degrees Celsius, which is 373 Kelvin. And we have that the ideal gas constant, the gas constant is just 8.31, should be pascals there, 8.31, and the unit for that is joules per Kelvin per mole, JK minus 1 mole minus 1, and we also have the atomic weight. AR is given by, well, the atomic weight of oxygen is approximately 16 plus 2 for hydrogen, so we have atomic weight of water is equal to 18. And so substituting these 4 numbers in, we get a density of 588 grams per meter cubed, but they seem to like kilograms per meter cubed. So substituting those all in and then dividing through by 1,000 to get the answer in a non-standard international unit for some odd reason, because they seem to like that in this textbook. So we get a density of 0.588 kilograms per meters cubed, and from the table, so that's the answer to the first bit of the question, is 0.588 kilograms per meter cubed. But from the table, so density rho table is equal to 0.598 kilograms per meters cubed. So why the discrepancy? And it's not a huge discrepancy here. So obviously an ideal gas law is designed to measure an ideal gas. It doesn't account for things like the size of the molecules involved, for example. The correction for that component is given, for example, by the van der Waals gas equation. However, for water, one of the things that this is really missing out on is actually the hydrogen bonds between the different molecules. So oxygen is a very highly electronegative molecule. So what it does is it drags the one electron for hydrogen. It leaves an extremely exposed proton, which has a very highly positive charge. And that positive charge is attracted to the negative oxygen molecules on different in different water molecules, and that strong bond causes the water to pack more densely, especially in water, but you see that in its gas forms, which causes it to be slightly more dense than slightly more dense than the ideal gas law would predict. So the reason for that discrepancy is the strong hydrogen bonds between the water.